Let's see. Where is this? By the way, we may have a different classroom, so I'll let you know if they change our classroom. I mean, I will send an announcement, but it would be still Livingston, obviously. So, but they might. So I'll keep you posted on that. So just to start with the topic from last time, what's the idea? We had a curve. So I have a curve here, and I want to rotate it with respect to the y-axis, right? And that will give me what's called like a solid of revolution, and I wanted to find the volume for it. So just to show you like the animation here, because it's kind of hard to do it on the iPad. Let's see. So that would be kind of like the solid of revolution, which by the way is called like a paraboloid. Not that it matters too much, but that's its name. And a paraboloid, yes, because sorry about that. Because like the idea, well, this curve is kind of part of a parabola, basically. It's like a concave down parabola. And when you rotate it, if you were kind of to make cuts with it, like that's actually something you do in Calc 3 if you ever have to take it. So if you make cuts with a plane, imagine just cutting this shape with a piece of paper. You get like like it would be like a parabola, like it's what you would call like a cross section. Yeah. So that's why it's called like a parabola. But again, like the name doesn't matter too much, but it's kind of like how it's referred to. Now, so we want to find the volume for this solid. So the idea, like that's kind of what I tried to explain you at the end of last time. Let me just go towards the beginning. The idea was like, do what you always do in calculus. You break up the region into pieces which are easier to understand. So kind of like the simplest thing to understand is like a rectangle, right? And so you kind of like think, oh, okay, what happens? Like the region can be made, you can regard the region as being approximated by all these like rectangles. So you focus on one of these ones, like, let's focus on this one, and then you start rotating that one about the y-axis. So when you start rotating it about the y-axis, like, well, I have to finish the animation for it to look a bit more clear. Like, is this going to, for some reason, this one doesn't show me like the, oh, let me see if there it is. If I rotate the rectangle about the y-axis, it gives me kind of like a hollow cylinder, which is called like a cylindrical shell. But that is easier to understand because what is the volume of that cylinder? And that's kind of like the last thing I had written last time. So I'll remind you like the formula in a moment. But the idea is like, the idea about the volume of like what's called like a cylindrical shell, actually. Well, basically it's like this area, the area of a rectangle is like the width times the height. The height, you think of it as being f of x. So, and the width is really, really small. That's what you call px. So like this is kind of like area. And the idea is like you have to take this kind of this rectangle and revolve it about the y-axis. And so by what amount do you have to revolve it by like an amount equal to the length or like the circumference of like this like circle that you see here. And the circumference of a circle is like 2 pi r. It's just like in this case, like the circle is like has radius x because that's kind of like the distance to the origin. It's like 2 pi x. And of course, like that kind of looks weird because like you usually just write like the x at the end. So that's like how it more the correct formula to write it. And then you integrate that because you're just trying to add up all the mini volumes, right? Like, so you kind of like start adding up all like those, all these like cylindrical shells, and in the limit, blah, 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 like that gives you like the volume of the solid revolution. So let me write that down on the iPad, but that is kind of like the main idea behind it. Is that making sense? Kind of like reasonable. So the advantage of these type of problems, and you'll see in a moment, in a sense, like the formula is more complicated than the ones we were doing with the cross sections, like the getting the discs, or like breaking, like cutting the solid. The formula is a bit more complicated, but it is easier in the sense that typically the function is just given to you. So it's a bit closer to just like a plugging thing. It's more like understanding like where the formula comes from, that takes a bit more like effort than the previous examples that we were doing. Okay, so let me share here, stop sharing here, and then share. Oh, sorry, yes.
So like zero, like the y.
Oh, so if you were let me actually I'm about to write it down in here, but see if this connects. So the idea is that for the bounds, and I'll do some examples in a moment, but if you had the graph, imagine that you had the graph of the function between some values, like they don't have to start at zero necessarily. So maybe there's here A and this is B. So, this is kind of like the area on the XY plane. That's like the thing that you start rotating up about the Y axis. But so like, like the area, like, like in this case, well, the volume, what I'm trying to say is like, it would be like the integral from A to B of 2 pi x times f of x dx, because this is like the thing that would correspond to the area, of one of these like rectangles. Which is kind of like, so for example, like basically, if you forgot about this term, that is literally like the formula for the area under the curve, right? You're just multiplying by 2 pi x because you had to rotate that with respect to the y-axis, if that makes sense. So like this is kind of like at a distance, just to make it more better on the picture. This particular rectangle is at a distance x from the y-axis, so that's why x is kind of playing the role of the radius in this picture, for like the rotation. Is that making sense? And so, sorry, just to explain this, like, so this corresponds to the volume. So this is like the volume of the solid revolution obtained by rotating. I'll just call this region R because, like, region R. Region R with respect to the y-axis. Why is it saying that I'm talking? Let's move this. Okay. And again, like in these problems, kind of one of the harder things to do. It does definitely, like, again, like the formula per se is just like applying the formula, because most of the times you are just given the function f of x, but like the visualizing what the solid looks like, not that it's needed, but it is like fun thing to try, and that definitely can take more effort than just like applying the formula. So let me give you like an example, which is still simple, but like already you'll see that it takes some like imagination to see what it would give you. But it's like a good first example to start with. So let's say I have the graph of y equals x. And again, I'll choose it. I'll choose 2 points A and B, which is here. So just like imagine that this is what I want to rotate with respect to the y-axis. I think this region is called like a trapezoid, if I'm not mistaken. Like, but like, so we want to find the volume. And by the way, this would say explicitly to use the cylindrical shell method. So I'll just let me put the name next to this formula. So this is called the cylindrical shell method, because as you saw in the animation, you're breaking the region into small shells. So like the problem would say something like use the cylindrical shell method to find the volume of the corresponding solid of revolution. So I'll give you a second to copy this, because again, I need to show you the well, what the solid of revolution looks like, but that's easier on like on an animation. So I'll kind of show you the animation. Because like in terms of like using the actual formula, okay, you have 2 pi x, that's always baked in. It's always the same in every time you find the volume. F of x is just x, so you would just put x here, right, and integrate that. So like in terms of like what the integration actually is, it's not too bad. But like actually knowing what that gives you, like in terms of the solid, it can be tricky. So let me see if I can show you that. Oh, so many open. Here you are. Okay. So that is the region, right, that I want to start rotating. Okay. So it's kind of like go piece by piece. So let me start with like the top. So like imagine, and then before I show you, like just imagine doing this in your heads. Like just imagine that you're about to rotate this part about the y-axis. Okay, so just imagine, but it just ignore the names of the like the axis, like like think of this as the y-axis if you want. It's just like this is like the only way I can do it on like the computer because I'm using GeoGebra. But just imagine rotating this with respect to the y-axis, which in this case is called the z-axis, and like think what it gives you. So I'll give you like 3, 2, 1 second. So let's see, and it gives you that. So that is what you get by rotating the top, like the ceiling. Okay, that gives you that, and then you have to imagine it kind of like it's a piece by piece thing. So now you imagine just rotating this like vertical line with respect to the y-axis, and again, try to do it in your heads, but that will give you like a small cylinder, which is like the cylinder radius 1. Where are you? Here you are. Okay, so you can see that. And so far, so making sense, kind of like again, it does take some imagination. And then imagine rotating this piece with respect to the y-axis. Where is like the other cylinder? Ooh. and then you get the other cylinder. So like, and now it's a bit messy, right? Like there's so many things like happening here, but essentially what you're looking at, like the solid itself, is kind of like the stuff like think of this as like this, it's like kind of like a room, right? Like, and the ceiling like is this piece, and the walls are kind of like cylindrical, right? Like, and the walls are between here, and this is like the floor. So the floor is still the floor. So like the regular one, like, so there's the floor. And so you're kind of trying to find the volume of that room, right? Like, so between the two cylindrical walls, like above the plane, like, and then below this like rooftop, okay? Um, it's kind of like this. Again, thankfully, you don't need to do this, right? Like that's like the power of the formula. You just like apply the formula, but it's still kind of nice to try to like see what it looks like, you know. If but it already tells you that for a line, you know, that was like rotating a line basically, and it already gives you something kind of like interesting. Like so, like you know, doing the rotations themselves is not that easy. Like you know, if you actually want to see how it looks like, so I do want to kind of like emphasize that. So the pictures are harder than the ones that we were doing earlier, but kind of like in a sense, like the formula is easier because you know, like the formula like it already gives you like the function, like you're more or less giving the function. So like it's just like applying the formula. But like the application of the formula is easier, but the picture is harder, like ironically. Okay. So and I won't even attempt to do that like on the iPad because like it would look horrendous. So you can just check like the video if you want to see it again. Um, or I can put like that animation online. I can also like add it to GeoGebra, so like you can find it on so yeah, like the volume itself is just the integral from A to B. I'm not giving particular values to A and B, so it would just be like the integral from A to B of 2 pi x that's baked into the formula. I'll put f of x in red just to emphasize. That's kind of like what changes from one problem to the next, you know. In this case, it's just like the regular straight line, y equals x, so I'll put x here. And that's just 2 pi x squared dx. And again, essentially 2 pi is like a constant. So what you're integrating is more or less x squared dx, right? So you get 2 pi x cubed over 3, and that is evaluated at x equals b and x equals a. So, you know, you can write it in different ways, but this is 2 pi over 3 times v cubed minus a cubed. And that is already good enough. Okay. That's like a good answer. So like, you know, like it's not like a particularly difficult integral, but you know, like the picture itself is kind of like interesting already. Is that making sense? Questions about the calculation? Is it okay with everyone?
Send like X. That's like.
Yeah. Oh no, I chose that. Like I just had to choose like a function that I wanted to rotate. So I wanted the function to be the straight line. You know, like that was my choice. So like the graph is given to you. More so like I just wanted something relatively easy to start with. So I wanted to start like I'll do like a parabola next actually. But for now I wanted to start with a straight line, and you know like there are many options for straight lines, but it was just easier to do like y equals x in this case. But you're right, like so it's usual like the worst you could have is that instead of like they giving you like the formula explicitly, in this case what they would tell you, well the function is the line that passes through this point and this point. Once you have like the 2 points, you find the slope, you know, like you find the slope, the intercept, and then you will find the equation of the line. But besides that, there are not that many functions that you can just find, you know, per se. So like you would just be given like the form, like the function in general. All right, I just wanted something simple to start with. Mhm. Right. Well, the thing is like, it's more like imagine like the area, you know, like let's say like you have this area and you have to sweep it out by 2 feet. So you would multiply the area by 2, right? Now imagine this area and you have to sweep it out this way, right? So you have to sweep it out by now what? Like the length that you walked or like the sweep out amount, but the sweep out is like the radius, like the circumference of the circle. Because like that's kind of like what gets moved, like if you think of my body as like being used as like the axis, that's what gets used to do the sweep out. Does that make sense? Right, exactly. Yeah. Yes. I mean, like again, like the point of all like this, the way we're starting with this particular topic is more to kind of show like the philosophy that you can use like an integral to find many different things and not exclusively just like area stuff. So like the point of like these examples, because actually I'll talk about length after I'm done with this, is more like, oh, like the integral is like a tool to whenever you want to break something into pieces and you understand those pieces and then you kind of like have to add them up together in some way, the integral is kind of like the tool to use. So it's more like to understand that, the integral is meant for like adding things in some way. More than like this more than like the specifics of these topics, because like for example, if you wanted to find volumes in general, you do what's called like a triple integral, which is what's called like done in multivariable calculus. That's kind of like the easiest way to do it. We're kind of like doing it like in a very it's kind of like with your arm twisted way, because like we have to always do like a single integral. But there's like a way to find volume called triple integrals where you do 3 integrals, and that's usually a lot more like simple like what we're doing now. But it's kind of more like the philosophy of like, oh, you want to know that you can use like the integral for like different things, not just like area or whatever. And why am I being so annoying with these like letters? Because like again, it's actually for like sanity check, because it's like, okay, so if you think of A and B as being lengths, B cubed and A cubed is like length cubed minus length cubed, and that matches volume, right? So I do want to kind of like keep track of those things so that you see formulas that are like a bit more like transparent in the sense that it's giving you the correct answer like that, because it does match the units the way that they're supposed to match, which gets lost if I just say that A equals 1 and B equals 2, because then you get 2 cubed, which is 8, 8 minus 1 is 7, and 7 what? Like since we don't keep track of units in mathematics usually. So it's kind of like an easier way to keep track of the units. Okay, so, but again, like these problems, like the nice thing about them is more like that it's just like doing the integral. It doesn't like involve so much like what we were doing before, where you do really have to do like a useful diagram, find relations between the variables and all that stuff. Like this is kind of like a slightly different perspective. So here's like another one, which is related to where do I have it here? Yeah, so this one is related to like the paraboloid, actually the original like animation that I showed you. Let's see. Okay, let's say I give you that parabola. So again, it is a concave down parabola, right? Because of the minus x squared, so that's why it's pointing that way. And then the reason why it looks this way is because, let's see, when x equals 0, the value for y is r, right? And then when is like the parabola going to intersect the x-axis? When does
intersect x-axis. Well, that happens precisely when you know, y becomes 0. So you said y equals 0. But what is y? Y is oh, sorry, I shouldn't have said, I didn't mean a 2 here. I meant r. Yes, like sorry about that. That should have been an r. Well, I'm being annoying again because I do want everything to come with the right unit. But like this has like units of area, and to force it to come to be able to do the subtraction, I had to put like something with units of length so that it cancels one of the units. So you see why we avoid units in mathematics, because then you have to be careful, keep track of many things. But it's kind of like nice, like for these problems to kind of do it that way. So you need this, and then that gives you r equals x squared over r, and that gives you that r squared equals x squared, right? And well, like that is like, you know, like the solution to that. There are different ways to do it, but I'm going to do it like just to emphasize some of formulas that you have seen before. You know, this is like the difference of square formula, right? So this is x minus r times x plus r. So like this intersects axis like a plus or minus r, okay? That okay, making sense, questions up to now. So the numbers come out nicely, well, in terms of R, because like, you know, it's R in kind of like all directions, like in the X direction and the Y direction, there's like an R. And then like, let's just say that I take these, like half of that region. And that is what I want to rotate with respect to the Y axis. So I'll call this region R. So the problem would be to find the volume of the solid, sorry, of the solid obtained by rotating R, the region. Oh, I mean, I should not have used like the letter R because like that was already used for something different here. So I'll call it I'll call it S because I ran out of letters. Just because like R I'm already using in the problem for something else. Is that making sense for a second? And again, like the problem itself, once you have like the formula for the function, the like it is just like the regular integral. Like in this case, like what you would have needed to find is like these points of intersection, because like that's where you would set up the bounds. So like the bounds would go from 0 to R, for example. So it's like solving this equation, what you would have needed to do to find the bounds for the integral. So in this case, the volume would be again like the integral from 0 to r of 2 pi x f of x dx. And then this would be the integral from 0 to r of 2 pi x. What was f of x? It was r minus x squared over r dx, if I'm not mistaken. And again, like, like the integral per se is not too bad. So like you can take out the 2 pi and then like you want to do two integrals, right? Like the integral from 0, oh, sorry, like, and then you have to multiply x on each term. So you would do the integral from 0, oops, 0 to r of rx dx. And then you can break it if you want, minus the integral from 0 to r, right? And then this x with this x squared gives you x cubed over r dx. That okay? Questions? Yeah. Right. That's the thing. Like, I don't know if it. Let's see. How should I do it? Right, but like, imagine that like the y-axis is passing through the middle of the tablet. So, if you use both, like the entire tablet, like both halves, then once I do like a 90-degree rotation, I'm already here, and once I do another 90 degrees, I'm already back to where I started. So when it's like both halves, I only need 180 degrees. Or if you do it with this formula, that's why it would come out as twice, because it kind of like, it's counting twice like the stuff, right? So that's why I'm only keeping one half. Like that's like a sort of point, but yeah, right, like it's a good like imagination thing to kind of like understand this happening. Um, any other questions? Okay, and then like the integral, like again, like all the integrals for these volume problems are not too bad per se, it's more like the setup or like, like finding the bounds or like whatever, but it's like the integrations, like typically they're just like the standard, like types of integrals, like they're like, most of them don't even require like a use up. So like later, after we're done with all these topics, we'll actually started to more like integration techniques. But for now, what is like the integral in this case? It's like, well, here you have to integrate x because r is a constant, right? So like the integral of x is x squared over 2. So you get r times x squared over 2. That gets evaluated at x equals 0 and x equals r. So that's easy. And the other one is like again, 1 over r is a constant, so you're just integrating x cubed dx, and that gives you x to the 4 over 4, right? At x equals 0, x equals r. And that's not too bad to evaluate because like the lower bounds are 0. So you get r cubed over 2, and then minus 1 over r to the 4 over 4. So like this will give you 2 pi r cubed over 2 minus r cubed over 4. And then you can do like common denominator, and then you'll get like, you'll find r cubed over 4, sorry, after you combine the two fractions. And that gives you, well, that gives you what you see there, pi r cubed over 2. By the way, like, sorry, I should have said that, like in this, again, I don't know if you remember like the GeoGebra animation, but like, oops, what happened here? Did I touch? No, go, came back to life. Like after you rotate this, you get like this paraboloid that I showed you earlier at the beginning of the class. So it's kind of like yeah, like a ball like turned upside down. Um, so this is like the volume, like this is, wow, output of paraboloid in case you want the name, but you don't need to know the name. So that would be the volume. Is that okay? Is that making sense? Questions about this? And so just to, before moving to like the other topic that I wanted to start today, okay. You can combine these in these two examples, like in the same way in which like Calc 1, when you were finding areas, you could find area between curves, right? So here you can find like like the volume between, like the volume obtained by rotating like the region between two curves, which sounds like a word salad, but like, I'll just do the picture and you'll see what I mean. So, and here I will use concrete numbers because like this is one of those cases where like the calculation would actually get messy if you just do it for like R without giving a specific value. So I'll kind of do like a combination of like the two examples that we did before. So like imagine that you know I have this parabola, but now as I was saying, I'll give this like a specific number. So I'll put R to be 2 because like otherwise like it would come out as a bit messy. So this is R squared over 2. Sorry, X squared over 2. So it is exactly the same formula that we just were working with, but again, you have to give a specific like, so this is 2, this was -2, and this was 2. Okay. And then let's say you had like the formula, like the line y equals x that we had at the big in the first example. So here you have y equals x. Okay. So there is some region between the two curves, right? There is a region between the curves, and so you want to find the volume of the solid. And that actually would be like I mean, that one can be harder to visualize if you try to imagine spinning this with respect to the y-axis and see what you would get. It's the more interesting shape. Um, so, but like, the way you should think about this is like, oh, this is actually similar to how you would find area between curves. When you would find the area between curves, you would just subtract the function. Well, I mean, you would do the integral of the difference, right? Between the functions. So here it's kind of like similar, you do the difference of the, so you can think of it as kind of like subtracting the functions, right? Or like subtracting the volumes like separately, right? Like integrate like for, if you call one f and the other g, it's kind of like f of x minus g of x, right? And so like that would just be like the difference in the two volumes that we found before. So like let me just put like some more like let's call this one f of x, let's call the other one g of x. Sorry. So it kind of works. What I wanted to do this example just to show you that it more or less works in the same way which like area between curves worked. So like the volume would be like the integral of like, and I like the important thing here is actually to find the bounds. I'll just write it a to b 2 pi x of like, f of x minus g of x. Right, so it's kind of like a difference of volumes. Right? So I'll just break it into two. So it's more like a difference of volumes formula, right? So in this case, is that making sense so far so good? How I'm doing this. So it really like it all boils down in this, like thankfully, that's why I kind of did the two examples earlier. We do have like the formulas for these separate cases, right? We had already done the integrals. So it's more like a plug-in thing. What we have to do is like plug in the corresponding values for A and B comparison with like the previous diagrams that we had. In this case, okay, it's kind of clear that A should go start at 0, right? Like that's not a problem. What is a little bit more interesting is to find the B. So that's why I wanted to do. So A in this case, sorry, here is A, right? And B in this case corresponds to this point, right? Because those would be the bounds of integration. So like A is not a problem, it's a 0, but B is kind of like a more like interesting calculation to make. So in this picture, in this problem A equals 0. And then well, how do you find B? No, it's kind of like in the same way in which you would find like B when you were doing like an area between curves problem. You just set up, where does this value occur? It occurs where the two curves meet. So it occurs at the intersection. So it occurs when both formulas kind of like give you the same value for y.
Is there any way you can give the G of X and X, or is that just?
Oh yeah, thank you. Like I forgot the X. Good catch. So yeah. Thanks. Oops, I forgot to multiply by X here. Thanks. Sorry about that. So right, so to find B, we intersect the curves, or like we said that the functions equal to one another. Find B, set functions equal to one another. So the first function was 2 minus x squared over 2, and then the other one was x. Okay, so how do you solve? It's a quadratic equation. How do you solve like a quadratic equation? It's kind of like annoying to have like it's nicer to have like the coefficient in front of x squared to be 1. So I'll multiply both sides of the equation by 2, just to get rid of like that 1/2. So that gives me 4 minus x squared equals 2x. And well, then it's, better to have like the x squared being positive. So I'll rewrite it like this, x squared minus plus 2x. So you need 4 to be, you need 4 to be x squared plus 2x. That okay so far? Making sense? Okay, now once you get to this point, and that's why I wanted to do this example, just to kind of remind you some basic like algebra things that are important in this class from time to time. So you have two options. Either you memorize the quadratic formula, right? And so you would move this to the other side, and it's kind of like I can write it, which is not what I'm going to do, but like that is like an option. You have like the quadratic formula that ax squared plus bx plus z equals 0.
gives you that x is minus b plus minus root of b squared minus 4ac over 2a. That's totally fine, like, you can always use that if you want. Usually, like for these problems, like if it involves a quadratic equation, I like it more when like, like a trick suffices and not just like using like a crazy application of the quadratic formula. So like the idea, like the trick in this case, if you didn't want to use a quadratic formula, is to realize, okay, x squared plus 2x, that actually is how like a certain formula starts, because if you do x plus 1 squared, that is x squared plus 2x plus 1, right? Like it's that kind of like this binomial thing. And so, if this, what I'm doing is more difficult to put it in square or the secret. And so if you subtract one from both sides, like, that gives you that x plus 1 squared equals, sorry, minus 1 is x plus 2x. Okay, so that, you can change it like this. Okay. So like here, I'm secretly using that, using like this identity that like, a plus b squared is a squared plus 2ab plus b squared. Good. And why is this nicer? Because then that gives you that 5 is x plus 1 squared, right? And that is easy to solve because you just take square roots, Um, so when you take square roots, like you get like a plus or minus. So you get plus or minus root of 5 equals x plus 1. And so, plus or minus root of 5 minus 1 would be x. But, we want the solution that's positive for the diagram to work. So like you have to use a plus solution here, because otherwise this would be negative and this would be negative. And so like the plus solution is root of 5 minus 1, which is what you would find also like if you were to use a quadratic formula. And that's actually where the quadratic formula comes from, right? You do like a similar trick to the one I just did. So it's kind of like a more elegant way to do it, but of course, like you can feel free to use a quadratic formula whenever you want. So this is like the one we want. Because it's positive. Questions about that? Okay, why did we need this value? Just because that was like the value that appears in the bound. So for our problem, what we're doing is the volume is the integral from 0 to that number, which is root of 5 minus 1 of 2 pi x times 2 minus x squared over 2 dx minus like integral from 0 to root of 5 minus 1 of 2 pi x times x dx. Of course, I'm not going to redo these integrals because we already have the formulas for these integrals from like the previous examples. As one of the advantages of like, having like the formula for like in terms of a or b or r, because then you can just like use it in many different circumstances. So I'll kind of put like the relevant diagram here. Let's see. Sorry, I need to copy paste a few things. So for the first one, let's see. Just to show you what I was using in each of them. So for the first problem, I'm using this diagram, right? Now R is root of 5 minus 1. So now here R is root of 5 minus 1, right? And we had found like the formula here for like the value for this volume. Sorry, just to go back up. That's really a nice thing about the iPad, that you can just do copy paste very simple, in a simple way. So the volume we had found was this. So we knew that the volume was this for the first piece.
which in this case, because of like this value of r, it becomes pi over 2 times root of 5 minus 1 cubed, which I will not expect you to simplify any further. That's good enough, like, at least for the first time. So that corresponds to this. And then the diagram for the next one, right? Oops, sorry to go here. Where do you, okay. This is where we had the diagram for the other one. And like here in this case, what we're like A was 0, right? And B is root of 5 minus 1, right? And the volume we had found, right? What was the volume in this case? Just to go back up, back. Where are you? Oh, here it is. The volume was this thing. That was the volume. And for these particular values, it gives you what? It gives you 2 pi over 3 root of 5 minus 1 cubed, right? And so those are like the two numbers that you're subtracting. Let me see something. Wait, let me check. Did I do all of this correctly? Sorry, let me check this because I don't know if you see what I'm seeing because like this coefficient, okay, this is pi over 2 is like 0.5 times pi, right? But two thirds, right? What is 2/3? Like it's like 0.66, right? The way I'm doing it, like this does look like, larger, like, this would come out negative, like, because you're subtracting like point, like it is the same, it is the same, you can factor out the root of 5 minus 1 because it is the same on both cases. Like, let me check because maybe there must be a problem with one of these coefficients. Like I can check quickly. Sorry about that. If anyone catches it, let me know because it should not be too bad to. I mean, this looks fine. And then 2 pi. Someone found something? Sorry, I'm just double checking quickly if I didn't do anything super silly. Um, feel okay, no, but this is fine. 2 pi. Okay, no. No, that's fine. Well, there must, oh, sorry, you found something?
Oh, yeah, it's plugged in like the, like, edge, like the into the radius, because technically that isn't the radius of the parabola, it's just the ends.
Oh, let's see. Right, like you're right, like in this case, like you needed, okay, right, because you're saying, yeah. Right, it would be more like, let's see. Yeah, like, oh my God, this is so annoying. Right, because if you have like the radius here, right? If that is like the what you're saying is like this this integral corresponds to this volume, like, but it doesn't include this piece, right?
Yeah, kind of, but like that, by setting like the radius in the final thing to be something that isn't like the actual radius of the parabola, then maybe then.
Right. No, I think you're right. Like, let's see, because I think like the problem is oh my God, yeah, like now I did make a mess because like right, like so like this show you like that you have to be careful with these formulas because right, like in the diagram, well, let's see, like, oh, right, like in this, yeah, exactly. Okay, so like the oh my God, thanks. Yeah, good combination, teamwork, because like yeah. So like it's better to kind of like right. It's actually better to decompose it correctly, so and not be crazy. Like let's see. So well, this was a more fun example than I expected. So right, like if you think about it as a diagram, oops, oh my God, like this is like a mess now. Okay, so what is happening as a diagram, right? Like in terms of what we're subtracting, yes. We have like the parabola here, which actually makes sense from the picture. Like in the picture, it kind of like was like okay, but I somehow like used like the you had this, right? But in that right, in that case, it is going to two, which is what you were saying, right? Yeah. And then you are subtracting. So well, crisis averted because of the things, but yeah, yeah. Right. And this one is the one, I mean, you did need like the intersection for sure, right? But this one is the one that goes up to root of 5 minus 1. So yeah, they do terminate at different points. Is that making sense? But it is a subtle point, right? Like, so you can easily kind of miss it, which is what I did when I was doing it earlier. So you have to, I mean, so that is why it's better to actually do the pieces like, separately, see what happens. So like just to fix that, so sorry about that. So here you do want to use R equals 2. Okay. So it is a subtraction of volumes, but you do have to be careful with the bounds, like, I like this example, yeah. Well, then that is easy. That's 4. It's definitely not done up to scale for sure. Wait,
Yes, that, because R was different in the first one.
let's see.
It's like the travel function of the triangle.
Right. Oh my God. No.
We just cut it off.
So okay, now what am I doing wrong? Let's see. So what is this kind of so confusing? Um oh, okay, but right. So sorry, what you were saying?
You like go down.
Oh, but let's skip like this one.
Yeah, so like, when you have the triangle. There's still like the little pieces of.
Oh, right. Yeah. You mean this piece?
Yeah,
Yeah, so like.
Ah.
so you need to do.
Right. And did we have like a formula for that one? No, right? Like we still haven't computed like just this piece of the.
Both of them from there, you got a ton.
So let's say you're saying right, like you're saying like like if I do these, oh my God, I'm so sorry about this. But like let's just focus on this problem because like it's actually like you know, good to see it happening in real time. So right, you're referring to this piece, right. So okay, good. That's fine. But then that is something you would also like to subtract, right? But then the question is, do we have like a direct formula from like what I had done before? I mean, I guess you could do like the integral again, like oh sorry, what you were going to say? Yeah.
Oh, well, yeah, to like back it up, I think what we did before, like, would work. The only issue is that we can't really do the substitution of the prior to over to like the parabola portion, just
Right.
because the R is consistent in this case.
Right. Okay, yeah.
So we just need to do the whole thing instead of being.
Right, I was just trying to break it into mini pieces, so like just like be able to right, like yeah, like the oh sorry, what were you going to say? Right. Yeah, so unless yeah, unless you wanted to break it into pieces like this, right? But sorry, what
So the washer method would have made to like not touch. The one, if the washer, well, like you wouldn't have a small R. So it's like the same method.
Right, like
They could do that separately or subtracted instead of just like. You don't subtract anything, it's like the R, the small R is zero. You just use the Y. Oh, yeah, okay.
oh you mean like like just to put like inside the well, but the washer is like isn't like the one washer with like pi like f squared minus g like with the squares, right?
It's just like.
Oh, okay, right. Yeah, okay. But I didn't want right, I just like I didn't want to do it that way. But okay, so this example, like right, I just wanted to see. I mean, I kind of like undershot it because right, I just wanted to like kind of like immediately be able to like use like the formulas from like the two previous examples just to combine them in a clever way. But yeah, you do have to be more careful with that. So I think I can just have to fix this example. So let's finish here, like, and then like I'll send like a fixed solution because like now I'm getting like on my head, like like how to do it the right way. But yeah, because like it wasn't going like the way I was thinking. Like so next time I'll start telling you about the like how to find the arc length, which is like a different topic about this. But yeah, like sorry about that. Like I just should have thought about a little bit better, like the diagrams here. So I'll kind of like send like a corrected version like at the end of the night. So, but I mean, it's kind of like we're kind of, yeah, like it's like a small fix, but for some reason I'm confused at the moment or something like that. She's asking.
Like a different approach entirely.
Mhm.
like, put everything into one.
Mhm.
That's just made us all.
Well, let me,